Hi everyone, this is Zainab rule number 49 and my topic is about software belief reliability growth model based on uncertain differential equation. Introduction. Software reliability growth models can be used as an indication of the number of failures that may be encountered after the software has shipped and thus as an indication of whether the software is ready to ship. These models use system test data to predict the number of defects remaining in the software. Most software reliability growth models have a parameter that relates to the total number of defects contained in a set of code. If we know this parameter and the current number of defects discovered, we know how many defects remain in the code. This is the residual defects for a test time, number of defects, residual defects, total defects, defects discovered. It is a graph showing the residual defects. Knowing the number of residual defects helps us decide whether or not the code is ready to ship and how much more testing is required. If decide the code is not ready to ship, it gives us an estimate of the number of failures that our customers will encounter when operating the software. Software reliability growth models are a statistical interpolation of defect detection data by mathematical functions. The functions are used to predict future failure rates or the number of residual defects in the code. Non-parametric reliability modeling. Hardware and software. In hardware we have wears of overtime increasing failure rate. In software do not wear overtime decreasing failure rate. These are the non-parametric reliability modeling. Hardware reliability modeling contains large independent random sampling. Model reliability make predictions. In software reliability modeling we have small observed dependent sample of size 1, not based on independent random sampling. Model reliability make predictions. These are the non-parametric reliability modelings. It contains hardware and software. Wears of overtime increasing failure rate, do not wear overtime decreasing failure rate. Hardware reliability modeling, software reliability modeling, large independent random sampling, model reliability, fake predictions, small observed dependent sample, not based on independent random sampling, model reliability, make predictions. These are the graphs of hardware reliability and the software reliability. It contains the maximum and minimum time estimated by the hardware reliability and the software reliability. It calculates the total time. Software reliability growth model data. First one is test time data. For a software reliability growth model developed during QA test, the appropriate measure of time must relate to the testing effort. There are three possible candidates for measuring test time: calendar time, number of tests run, execution CPU time. It is the test time data in software reliability growth model data. Defect data. It contains major, can tolerate the situation but not for long. Solution needed. Critical, intolerable situation, solution urgently needed. Group data, the amount of failures and test time that occurred during a week. These are the defect data and group data in software reliability growth model. Test time data for a software reliability growth model developed during QA test, the appropriate measure of time must relate to the testing effort. There are three possible candidates for measuring test time: calendar time, number of tests run, execution CPU time. Defect data measure can tolerate the situation but not for long solution needed. Critical intolerable situation solution urgently needed. In group data, the amount of failures and test time that occurred during a week. This is the defect data and throughput data. Software reliability growth model types. Software reliability growth models have been grouped into two classes of models, concave and S-shaped. The most important thing about both models is that they have the same asymptotic behavior. The defect detection rate decreases as the number of defects detected and repaired increases, and the total number of defects detected asymptotically approaches a finite value. The most important thing about these both models is that they have the same asymptotic behavior. That is, the defect detection rate decreases as the number of defects detected and repaired increases, and the total number of defects detected asymptotically approaches a finite value. This is the graph showing that concave and S-shaped models. The concave model is contains the concave vertex. One side it is test time and number of defects, and the test time is S-shaped, as we can see in the graph. One side number of defects and another side is which is test time. It's showing the concave and S-shaped models. The table showing the software reliability growth model examples. It contains the model name, model type, name of team, reference and comments. For the models, Goel Okamoto, GOS shape, percentile, component, Pereyo, and the model types of these are concave and S-shaped. It is the Goel Okumo GO model, and the formula for this is mu of t is equals to a of L minus E cap minus B at t, where a is equals to expected total number of defects in the code and b is equals to shape factor is equals to the rate at which the failure rate decreases, that is the rate at which we approach the total number of defects. The Goel Okamoto model is a concave model, and the parameter a would be plotted as the total number of defects. Basics assumption of Goel Okamoto model. The execution times between the failures are exponentially distributed. The cumulative number of failures follows a non-homogeneous Poisson process NHPP by its expected value function mu of t. For a period over which the software is observed, the quantities of the resources that are available are constant. The number of faults that are constant. The number of faults detected in each of the respective intervals is dependent for each other. This is the basic assumptions of Goel Okamoto model. As we see in the figure, the execution times between the failures are exponentially distributed. The cumulative number of failures follows a non-homogeneous Poisson process by its expected value function. For a period over which the software is observed, the quantities of the resources that are available are constant. The number of faults detected in each of the respective intervals is independent of each other. And the summary is software reliability modeling provides useful measurements for decisions, does not require expert knowledge of the math, is relatively easy with the use of software tools. Fault correction improvement adapts model to be more like software. Demonstrate combined use of traditional SRM tools with spreadsheet technology. Non-parametric modeling. New approach shows promise. Prototype to be expanded. This is the summary of the topic. That's all about my topic. Thank you.